Hello everyone, welcome to Sri Chaitanya Academy. Now let us talk about the transition course which we are running very actively on Sri Chaitanya Academy YouTube channel, and let us now come to chemistry. The last session was of physics. Now in this transition course we have reached a point where I have discussed to you about the periodic table, and many important aspects of the periodic table are also discussed, right? So now I'm going to move to something which is an application of the periodic table, how periodic table helps us to predict periodic properties. One of the most important periodic properties are ionization potential or enthalpy or energy, electron gain enthalpy, electron affinity and electronegativity. Let's dive deep into each of these. Very easy, not very difficult. If you understand the concept, connect the dots, then this is a piece of cakewalk. Now let's get started. Yes, this is the periodic table. Now every time in my slides you will see the periodic table, because this periodic table is the crux of complete chemistry that we are going to discuss, right? So now have a great look at this. Get the picture in your mind. Let's move forward to the first property, ionization energy. So what is ionization energy? Let me first give you the definition, right? It is the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom to infinite distance. Right. So, little complicated, but actually it is not this complicated, right? So, how will you understand this? Simply, if you have a atom like this, you have these shells, right? And then you have an electron lying here. The outermost shell is called the valence shell, correct? Now, understand that this electron is being held, right? It is being held, it is being kept in orbit by the attraction which is happening here, right? Due to the attraction here. It's like a glue, right? It's like a glue which is holding this electron in the orbit. Now, if you need to grab this electron and remove it from the clutches or from the hold of the nucleus, then you need to put energy. Why you need to put energy? Because you need to apply a force in the opposite direction to the attraction of the nucleus more than this attraction, right? Now I am removing this electron, I am applying some energy, right? Now we will add the specific thing. Now, after removing this, I have to remove it till where? Till infinity, till infinite distance. Now, why infinite distance? Well, we can be 100% sure that at infinite distance, the influence or effect of the nucleus is 0 on the electron. There is no attraction on this electron, right? So, now this was the process. Moving forward to what kind of atom? The atom is an isolated gaseous atom. Isolated means alone, gaseous means in the gaseous state, and an atom. So what I am trying to say is that if you have sodium metal, suppose you have a piece of sodium metal like this. Now this piece of sodium metal will have a number of sodium atoms, correct? Plus, this is in which state? Solid. So to calculate the ionization energy, first what you have to do is, first you have to convert this solid into gas. Even now in the gas phase, there is a collection of sodium atoms. There are many sodium atoms, right? So from this collection of sodium atoms, right, you have to take what? You have to take a single sodium atom. Only one sodium atom separately from this, isolated, alone. No other sodium atoms are there with this. And this is what? A gas, in the gas phase. Now, if you remove electron from the outermost shell of this isolated gaseous atom, then the energy that you need to give to take this electron to infinity, that energy is ionization energy. Please understand this very carefully, right? Before we move on to the factors affecting ionization energy, let me take another slide and explain you something more. So think about it. Suppose I have this. 1 minute. Let me take. Right. So now suppose, understand this. I have a metal. Suppose we take potassium. Okay, potassium metal is there. Solid. Going to potassium plus, right, suppose in the gas phase, and it loses one electron, right, and energy that is released out, suppose 394 energy you have to give, sorry, kilojoules. This much energy you have to give. I am supposing that. Now moving on to the next case. What is the next case? Gas. Gas. Again electron is released out. Now the energy is plus 100 kilojoules. Tell me the ionization energy of potassium. This is a question in front of you. Tell me the ionization energy of potassium, which it will be. Is it the first one or is it the second one? Put it in the chat. Everyone, put it in the chat. Is it the first one or is it the second one? Which of this is the ionization energy of the potassium? Is it this? No. Why it is not this? Because this is a solid atom. It is solid. But this is most surely ionization energy. So the ionization energy of potassium will be 200 kilojoules per mole. Sorry, here put per mole. Right. So remember, it has to be an isolated gaseous atom. Right. So after you have understood this, what is ionization energy? Let us move on to the factors affecting ionization energy. How will you see the factors affecting them? Size, right? How does size affect it? So suppose you have an atom. One atom is like this. This is the valence shell of this atom. And one more atom is there like this. And both of them have an electron in its valence shell. Remember, this is just the valence shell, right? Right. Tell me, you have the first case and you have the second case, where the ionization energy will be higher. Remember, if I am talking about ionization energy, remember I am talking about the energy required to remove this electron to infinity, right? So please put stress on your brains and tell me where the ionization energy will be higher, more ionization energy, where it will be required. Take some time, whoever has joined in. where the ionization energy will be higher? Tell me. See, ionization energy you are putting in against the nuclear force. Now here, see, the electron is closer to the nucleus. So the attraction by the nucleus will be higher, right? Here attraction will be more. Now if the attraction by the nucleus of this electron is more, it is holding it very closely, it will be difficult for you to put force in the opposite direction and remove electron, correct? So here you will require more ionization energy, more energy you need to put. Here, because now it is a larger distance, because you are far away from your enemy, the effect of your enemy on you is less. So this is your enemy, this is you, distance is far, effect is less. So here you will have less ionization energy. So this distance is essentially what? This distance is size. So if I talk about how does ionization energy depend on size, simple, ionization energy, see, it is more when the distance is less, it is inversely proportional to size, right? It is inversely proportional to size, right? Now moving on, how does it affect, how does shielding affect this? Shielding I have already talked about in previous lectures, right? I am not going to repeat it, but I am going to repeat one aspect of shielding, which is when you have this is the valence electron, suppose this is the internal electron. So this electron shields the outer electron from the nucleus's pull, right? Understand that if shield is more, if more is the shielding is more, then this outer electron will feel less nuclear charge. So I can say that Z effective is less if shielding is more. If nucleus's pull is less, so I can also say that nuclear pull is less. If nuclear pull is less, then it is easier for you to remove the electron, right? Easier means what? What work or what job is easy for you to do? Which consumes less energy, right? So the ionization energy will be less. Shield more, ionization energy less. So can you tell me the relationship between them? I can say that ionization energy is inversely proportional to shielding, right? Now, next is the penetration power. Penetration simply means how close is the orbital to nucleus, right? Out of S, P, D and F, if I talk about, if this is the nucleus, right, for the same value of N, right? If you have 3S, 3P, this will be 3D, sorry, 3D, right? So, sorry, this will be 3D, right? So you can see the distance of 3S is less, means the penetrating power will be in this order, 3S, 3P, and then you have 3D. Now, more closer is the orbital to the nucleus, more closer is this orbital to the nucleus, more closer it is, stronger is the force that it will feel, right? So this, this is the penetration power. Now, because it feels a stronger force, then it is a hint for you, stronger force of attraction because it is close, stronger force of attraction means it is difficult for you to remove. Difficult means you have to give more energy. So again, the ionization energy order will be in this order. This is the ionization energy order. So I can directly say that ionization energy is directly proportional to the penetration power. Of orbital. This you can take as your mantra, right? Right. So after we have done this, let's move on to the next factor, which is the electronic configuration. To understand this, let me remind you that one minute. If you remember, right, fully filled is more stable than half filled, which is more stable than partially filled configurations, right? So how do I understand this? Let us talk about first nitrogen and oxygen, right? Out of nitrogen and oxygen, right, who will have higher ionization energy? What is the configuration of nitrogen? 2s2, 2p, 3, 2s2, 2p, 4 for oxygen, right? Now understand this very carefully, that this is a half filled configuration, right? And this is a partially filled configuration, right? Because half filled configuration is much more stable, because this is much more stable, something which is stable, you require more energy to disturb that stability, right? So because it is stable, you will require more ionization energy, right? So I can say that ionization energy for nitrogen will be more than ionization energy for oxygen, simply because oxygen has a half filled configuration. So let us see that ionization energy is directly proportional to stability of configuration. Remember this effect as well. We will get to that. This effect comes into full blown power when you are having your period, right? We will discuss that later, but understand this now, that electronic configuration has a profound effect on ionization energy, where the fully filled is more stable, next you have half filled, then you have partially filled. Moving on. Now variation along groups and periods. I will take first the variation along period, and in the period I will take which period? I will take the second period. If you talk about the second period, this is your second period. Second period. Right. Now, 2 to 3 things here. If I talk about general variation, as you are going from left to right in a period, like this, what all things are happening? Let us write the configurations here. 2s2, two s1, right? 2s2, 2s2, 2p1, 2s2, 2p2, 2s2, 3, 2s2, 2p, 4, 2s2, 2p, 5, and you have 2s2, 2p, 6. Right? The configurations are done. Now, as you are moving from here to here, see what is happening. This 2, 2, 2, 2, 2 is remaining the same. So, I can say that electron is added to the same shell. Now, what do I mean by electron is added to the same shell? I mean that if there is a nucleus, this is n equals to 2, electrons are getting added to approximately the same distance. So, the distance of the nucleus and the outermost electron, that distance is not changing. But there is something else changing. What is changing as you are going from here to here? If we talk about the atomic numbers, this is 3, 4, 5, 6, 7, 8, 9 and 10. Atomic number means what? Number of protons is increasing. As number of protons increases, the positive charge on nucleus increases. Now, positive charge on nucleus increasing means what? It means that nucleus's power to pull electrons, that is increasing, right? So, nucleus is now able to pull. So, as you are moving from here to here, what is happening? Nuclear pull increases. Now, as the nuclear pull increases, now the nucleus is pulling it very strongly. You have to put more energy to remove it. Ionization energy. One word I am writing here, generally increases. Why I wrote generally? You will understand. So, the order of ionization energy generally without any anomaly or any disturbance should be how? It should be like this. So, as a matter of fact, if you are trying to find the ionization energy order, my suggestion would be first follow this kind of a principle and logic. After this, you have to do something else also. Let me take one more color. Now, after you have done this, notice the configurations which are either fully filled or are half filled. See, this is fully filled or vital, and this is half filled, right? This is fully filled. Wherever you are having fully filled or half filled configurations, simply I am telling you to do what? The arrow which comes after that configuration, just invert that arrow. So, this is the fully filled configuration, invert this arrow. So, this arrow becomes like this. Similarly, here also half filled, invert this arrow. So, this is your actual order of ionization energy. So, this is your actual ionization energy order. Right. Simply follow this rule, draw it out the way it should be. Across a period, the ionization energy should increase, right? But now you put in the half filled, fully filled logic, invert the greater than signs, you will get the ionization energy orders like this. Now, variation in a group. So, I have specifically taken the 13th group. Why I have taken that? That will become clear as we move forward, right? 13th group is which one? This one, I think. Right. Configurations, yes, configurations are important or not? Okay. Okay, let us write down the configuration, nothing big in that. 2s2, 2p1, 3s2, 3p1, 4s2, 4p1, 6s2, 6p1, 7s2, 7p1, right. Remember that gallium, here there are 10 d block elements, and at thallium there are 14 f elements, right. Remember that. Now let us do what we want to do. As we are going down the group, what all things you will notice. Now you can see that this n number is changing, and as this n number changes, the distance from the nucleus changes. As the distance increases, so going down the group, I can say that distance of valence electron from nucleus increases, correct. Now what else? The atomic number is also increasing, right? As you go down, the Z effective also increases, but distance dominates. Distance is the dominating factor. Yes, atomic number is increasing, number of protons are increasing, but the distance increases by so much large amount that this increase becomes insignificant, the nuclear charge increase. So distance dominates. Now as distance increases, what is happening? The nucleus pull, nuclear pull decreases, and as nuclear pull decreases, it is more easier for you to remove the electrons, right. So your ionization energy, again I will say, generally decreases. Why I said generally? Because it is not the actual order. In group 13, understand this here. Now the actual order, now what should be the order actually? If you talk about, let me just take one more slide. So the actual order should be what? Tell me. This is going down the group, ionization energy decreases, so the actual order should be right. Now what happens is, at gallium you have the d block and thallium you have f block. Now d orbitals are poor shielders of electrons, correct? D orbitals are poor shielders of electrons. So then what will happen? Simple. This will feel an increased pull of electrons, increased pull of nucleus on the electrons. If the nuclear pull is more, this will have a higher ionization energy than aluminum. So simply switch these in position, right? Next, F block contraction happens here. Understand that F block elements are much more spread out than D block elements. Because they are much more spread out than D block elements, because of that, what happens? They are poor shielders of nuclear charge, and nuclear charge is not shielded properly. So nuclear charge is felt more by the outer electrons. So this has a very high Z effective, due to which you will require more ionization energy to remove electrons from this. Now that is one thing. The second thing is, because F orbitals are much more diffused than the d orbitals, its contraction is also more. So F block contraction is more. So this thing shifts from here to somewhat here. So the actual order becomes like this. This is your experimental ionization energy order. This you can remember based on what? This you can remember based on a mnemonic which I say, which is battle gain, right? Battle gain, right? If you do this, through this you can understand that, right? So now let us move on. Successive ionization energies, what do I mean by that? Let us get to that also. Suppose I have aluminum, right, in the gaseous state. Aluminum loses an electron. So the energy change for this process will be ionization energy 1. Now aluminum plus in the gaseous state loses the second electron to give you aluminum 2 plus, second ionization energy. Then aluminum 2 plus goes to aluminum 3 plus to lose another electron. This will be ionization energy 3. If I ask you the order of these ionization energies, these are called successive ionization energies, means one ionization energy after the other, right? So can you tell me the order of this? Understand that this positive and 2 plus means that nuclear charge is increasing much more than the negative electron charge. So here I have already told you the cation always has a higher ionization energy than its neutral part, and as the positive charge increases, the ionization energy increases. So you can write this down, ionization energy is directly proportional to the positive charge. So you can see what you can tell the order of ionization energy is. Right? This you try as a homework, we will see it whether you are able to do it or not. Now next is electron gain enthalpy. What is that? I will give you the definition afterwards, but let us first understand what it actually is, right? So electron gain enthalpy. Is whoever is watching me able to hear me clearly? Say yes or no in the comment section. Are you able to hear me clearly? Say yes or no in the comment section. Okay. Let us talk about electron gain enthalpy. See, what was ionization energy? That you had a nucleus here, you had a valence shell, and you are giving, okay, good Vaishnavi. So now I am using my energy to remove this electron out, right? Now where I am removing this electron to? Infinity. This was ionization. What is electron gain enthalpy? The opposite of this. Now what I am doing is, I am putting electron back from infinity to valence shell. Now for removing electron you had to give energy, correct? You had to give energy, which was your ionization energy. So now to put back electron, for removing electron you had to give energy, for putting back electron you have to lose energy. So this is lose energy, and this energy which is lost is called electron gain enthalpy, right? Remember, now I am going to give you the definition. So electron gain enthalpy is the energy released when an electron, right, when an electron is added to the valence shell of an, again the same word, isolated gaseous atom, isolated gaseous atom from infinity, right. This released word you can also change by energy or energy change, right. Why I said change there? Can you think about it? I'll tell you why I said change there. Because there normally energy is released, but there are certain atoms where energy is actually needs to be given to add electron. Those are noble gases. Why? Because noble gases have a complete full octet configuration, right? They have NH2 NP6 configuration. Octet is complete, so they don't want to gain any electron. So they will have positive electron gain enthalpies. Positive means, positive in chemistry means you have to give energy. It is an endothermic reaction. Normally electron gain enthalpies are negative, right? These are exo reactions. For noble gases it is a endo reaction. You have to give energy. So that's why I have written here change. It can be positive also in case of noble gases, right? So now let's move forward towards another similar term called electron affinity. So what do we mean by electron affinity? Simply put, electron affinity is negative of electron gain enthalpy. Or in affinity, affinity means what? This affinity word means what? Attraction for electron. More is, just think in your mind that is attraction of a particular atom more for electron, then electron affinity is high. So it is simply electron affinity is what? It is the attraction for electron. More is attraction, more is attraction, more is electron affinity. And remember this, only electron affinity and electron gain enthalpy are numerically equal, but they have different sign. So if I tell you this, that you have this someone, and here I gain an electron and I get this anion I get, then the enthalpy change for this will be electron gain enthalpy. So suppose this electron gain enthalpy is around minus 50 kilojoules per mole. If I ask you, tell me the electron affinity for this, then you will write that electron affinity will be plus 50 kilojoules per mole. Got it? Right. Now factors affecting electron affinity, this is very easy. If you see distance as it increases, now here this is opposite to ionization energy, remember that. As the distance increases, the nucleus's pull is decreasing. Now what is the nucleus? What are you doing? You are adding electron into this. If the nucleus is helping you to add electron, it is easier, right? Right? So what will happen? If it is easier, then what will happen? More energy will release out. Understand this? If it is easier, more energy will release out. So electron affinity is directly proportional to, if the size is less, the attraction is more, right? If it is electron here you are adding, it will be much more easier for you to add electron because nuclear is pulling from the opposite side. So this electron affinity is directly proportional to Z effective, which is inversely proportional to the size. Remember this. This is the effective nuclear charge, right? I already told you electron affinity is directly proportional to Z effective because this Z effective helps in adding electron, right? Screening means what? We know that screening is inversely proportional to Z effective, right? It will reduce the nucleus's pull. Now because it is inversely proportional and Z effective is directly proportional to electron affinity, so I can also say that electron affinity is inversely proportional to screening. If any one of you do not understand this, please see the previous videos, right? Now, electronic configuration, again the same funda, that fully filled configuration is more stable than half filled. Then you have partially filled. Is inversely proportional to the stability of the configuration. So electron affinity order will be what? Fully filled will have the least electron affinity. So this is also, now if you talk about the electron affinity order, fully filled will have the least affinity, then you have half filled, and most affinity will be for partially filled, right? So like this you can arrange them. Group 16. 16 group is which one? Right? This is from the second period, third period, fourth, fifth and sixth. Understand this very carefully, what happens here. Oxygen and sulfur, or the previous one, oxygen has a very small size. Suppose this is the oxygen's nucleus, right? And this is the valence shell. So if you have an electron in us, and how many electrons are there? What is the configuration? 2s2, 2p, 4. Already 1, 2, 3, 4, 5, 6 electrons are here in such a small space. Imagine you are in a small room which has very small room where all of you are put together, right? 6 of you are put together, right? In that small room. Right? This is that small room. If a 7th member is made to come into this small room, what you will do? You will push that 7th person out, saying there is no space because the room is small. Same thing here also. If you try to add one more electron, which is the process of electron affinity or electron gain enthalpy, it says please go out. So you will get high electron repulsions, due to which what happens? The electron affinity of oxygen decreases, right? How much? Well, a lot. This oxygen shifts to back, right? It shifts back. Normally what should have been the order? As you go down the group, the distance increases from the nucleus, so electron affinity should decrease. Normally oxygen should come somewhere here like this, but because of this it is shifted from here to here, and the order is this. actual electron affinity order for this group. Group 17, simple group 17 is halogens, so you have fluorine, chlorine, bromine, iodine. Here also the same effect happens. Normally electron affinity order should be fluorine, chlorine, bromine and iodine. But due to small size of fluorine and electron-electron repulsions, you can write due to small size of fluorine and electron-electron repulsions to incoming electron affinity of fluorine is less than electron affinity of chlorine. So these two switch positions and the actual electron affinity order is this. Okay, right, this is the electron affinity order. 16th group is done. Electronegativity. Now what is electronegativity? It is the tendency or power of an atom in a bonded situation to pull the shared pair of electrons towards itself. What I am trying to say is that suppose I have here A and B. Normally, if it is a pure covalent bond, what will happen? These two electrons which are being shared will be in the middle, right? Exactly in the middle. But what if this B has more power to pull electrons? So it will pull electron towards this side. Now how the situation will be? The electron will be more closer to B, right? Now the next situation, if B is too much powerful, what will happen? These electrons will totally shift on B, right? And what you will get? You will get a cation and you will get an anion, right? This is a situation of a pure covalent bond. This is a polar covalent bond. And this is a ionic bond. Right? Now because see, electron if completely shifts on B, you will get a complete negative charge, right? One negative. This is -1. But if little bit only shifts, little negative. That little negative is denoted by delta negative, and little positive, because A has given, is by delta positive. So electronegativity is talking about this situation, right? So what you will see here, we will say here that electronegativity of B is higher than electronegativity of A. That is what I will say. And electronegativity is represented by a symbol like this. Draw a line like this and then draw a line like this. This is pronounced as chi. CHI, chi. It's not X, it is chi, represented by this. Right. Now factors affecting electronegativity, pretty easy. Electronegativity is what? You're pulling, right? So suppose you have HCl, chlorine. Why? Because chlorine is moving towards end of the period, right? It is in the end of the period. Because it is the end of the period and the as you're moving from left to right, so let us understand that also, period 1. So this is your, so as you're moving from here to here, what is happening? The Z effective increases. As the Z effective increases, nuclear pull increases, right? As nuclear pull increases, what? Ability to pull electrons increases, so electronegativity increases, right? Now same size, electronegativity, if the size is increasing, what will happen? If the size is small, it can easily catch electrons, that is electronegativity. So chi is inversely proportional to size. Oxidation state. Oxidation state you will learn, it is the positive charge, right? If the element has a positive charge, it can more easily pull electrons, so it is directly proportional to positive charge. So chi is directly proportional to charge by size. This we can easily write. Configuration, pretty simple. No, this is something which does not belong here. Why it does not belong here? Because this is the only property that does not depend upon configuration. So write it down, does not depend on configuration. Write it in, highlight it, that electronegativity is the only property that does not depend upon configuration. Now, electronegativity, there are many scales, but I will talk about the Pauling scale. Pauling, just like that, in his mind, gave what? Fluorine, which is the most electronegative element. An electronegativity value of approximately 4. And all other elements in relation to fluorine were given electronegativity values. So you can see this value: fluorine, oxygen, chlorine, nitrogen, bromine, iodine, carbon and hydrogen. The values are not important, but what is important is the order of electronegativity. You should need to remember. Don't think that after fluorine, chlorine will be more electronegative. No, the order is most electronegative fluorine, then oxygen, then chlorine, then nitrogen, then bromine, then iodine, then carbon, and finally hydrogen. So this is the order of electronegativity. Remember this, by heart this. This will be not only useful in inorganic chemistry but also in organic chemistry. This order is important. Fluorine is the most electronegative element, followed by oxygen. Applications of electronegativity difference, simple. Understand that this electronegativity difference is defined as B minus chi A. If B is more electronegative than A, right? If this electronegativity difference, there are few cases, is less than 1.7, it is less, then the compound is 100% covalent compound. Second, if this electronegativity difference, सर आप हिंदी में क्यों नहीं पढ़ा सकते, क्या इतनी इंग्लिश समझ नहीं आ रही? ओके, मैं पढ़ा सकता हूं हिंदी में, पर based on this platform we have to teach in English, right? That's the reason. If you want to get me in Hindi, you can sign in the Telegram channel and fill the Google form where I will get in touch with you personally, and there you can ask me whatever you want in whatever language is feasible. Now, electronegativity difference, when it is more than 1.7, the compound is 100% ionic. And third, when electronegativity difference is equal to 1.7, the compound is 50% ionic plus 50% covalent, right? Through this we can use electronegativity differences. Similarly, it is also used to find the percentage ionic character. How do we do that? There is a formula, plus 1 minute. Here it is 3.5. Right? This gives you the percentage ionic character in a covalent bond. Right? So this I was talking about. If you want to get in touch with me personally, then fill this Google form. I will reach out to you and help you out personally, right? If that is not enough, scan this, join the Telegram channel where we will bring you future and further updates about what all things are happening at Sri Chaitanya Academy and a bunch of free worksheet and free stuff that will help you ace your examinations and also get a head start in 11th. So bye for now from my side. Next we have an exclusive maths session for you, right? So stay tuned, keep time, scan these up, fill these forms till I meet you again in the next class.